Okay, we have talked about how we describe a material flowing into and out of a compartment, but what if we have more than one pollutant? Our short answer is that when we have multiple pollutants, we are going to deal with each pollutant one at a time. And usually this is going to be an okay strategy because at least initially we don't have to worry about our pollutants interacting with each other. There might be a time where we need to get to that complexity, but for right now anyway, we don't have to worry about it. But the other thing that we can have is a situation where, okay, so let me make sure this is clear. Multiple pollutants. Yes. But if we have multiple sources of the same pollutant, we want to be able to combine these effects. So we do add them up together. So if we have multiple flow, we might have multiple places where they flow in and they are going to give us a total amount of flow. We also can look at each of their rate constants. So each of these are going to add up together, which means that since there is an inverse relationship between the rate constant and the residence times are going to have an inverse relationship when they add up. So this is just coming from inverting each one of these individually for their residence times. And of course, presumably, each one of these is probably, well, I guess it depends, right, on what the source is for that pollutant coming into or out of the system. So as long as the compartment is the same stock, then we can consider them all together. So the easiest way for us to think about these kinds of more complex situations is just to go ahead and look at a bunch of examples. So let's look at a slightly more complicated example. So in this example, we have a room, maybe a garage, and we're going to assume it's not too big, so like 40 cubic meters, which is about the size of a one-car garage. And let's imagine that this particular garage has a residence time for air in this garage of 3.5 hours. So it's leaky. Or I guess I should say it's ventilated, right? It's a feature, not a bug. So this is a 40 cubic meter volume. This is our residence time. And we have a pollutant. And the pollutant is maybe coming from a car or a lawnmower in here, and it's going to be carbon monoxide, which we know is a toxic gas that we can't detect with our noses or with our lungs. So and carbon monoxide comes from incomplete combustion. So this is why you don't want to run your car in a garage with the door closed, just in case your car is not burning efficiency. So let's imagine that this is being produced at a rate of 15 grams per hour. And that means that we have this rate at which this material is coming in to the garage. But carbon monoxide is a fairly reactive gas, so it reacts at a rate of 5.6 times 10 to the minus 5 per second. So what we might ask is, what is the concentration of the carbon monoxide in the garage over time as we allow this lawnmower or car to be running so that we reach a steady state? So at steady state, what is the concentration of the carbon monoxide? Okay, so let's think about this for a minute. when we've talked about our different variables, we've talked about flow, and we've talked about residence time, and we've talked about rate constant, we've talked about concentration, we've talked about amount of stuff, and volume. And we have a bunch of, well, we don't have a bunch of, we have a couple of equations that we use to relate these. So let's review those. So I'd like you to pause the recording for a minute and go and look back up in your notes from last time what these relationships are. Okay, so hopefully you had a chance to review this and to remember that the flow is equal to the amount of stuff over the residence time, or you can also think about it as the amount of stuff multiplied by the rate constant. And the concentration is the flow multiplied by that rate constant divided by the volume. Because the concentration times the volume is going to give you the amount of stuff, just as background. Okay, so hopefully you remember those relationships, and now we can go forward with the rest of our calculation here. So if we want to know the steady state, then what we're really asking for is the concentration for the amount of carbon monoxide we have in our garage. So we want C. Okay, so let's think about those numbers that we have. So if we think about the production of the carbon monoxide from combustion, then we can think about that reaction, which has a rate constant, which we said was 5.6 times 10 to the minus 5 per second. And if we think about our other rate, it's in hours, so maybe let's go ahead and convert those. So I'm just going to convert seconds into minutes, and then minutes into hours. And this becomes 0.2 per hour. All right, so this governs our rate constant for the chemical reaction to decay the carbon monoxide chemically. And now we want to pay attention to how much or what the rate constant is for the air or the carbon monoxide to just disperse out of the garage. So this is where it's leaking out of the garage. So I want to just remind you that what we're measuring here, this is not the production of the carbon monoxide. This is how quickly the carbon monoxide disperses out of the garage. That's what the residence time is. It's saying how long before it exits the garage or how long before it's broken down. So that is what we are calculating right here. So if we think about the dispersal, we have, let's see, what did we have? We had the residence time for the air in the garage, and the residence time for the air in the garage should be the same as the residence time for carbon monoxide particles in the garage too, that they will naturally just migrate out of the garage just like the rest of the air does. So we can say that this is equal to the reaction rate of the air, which should be 1 over the residence time of the air. And that number, just a moment ago, here we had 3.5 hours. So we have 1 over 3.5 hours. And if we do that math, we should get 0.29, and then we have 1 over hour units. So as we saw a moment ago, our total rate constant is equal to the sum of all of our rate constants. So let's just go ahead and add those up. So we have 0.20 plus 0.29, or a total of 0.49 per hour. being carried out or broken down. So this is a total rate constant, but what are we looking for? Remember, we have to kind of stay on target. So we're looking for the steady state concentration. And if we scroll back up to those equations, because we're not totally familiar with them yet, we need to remember that concentration is the total flow, or excuse me, just the flow times the rate, or the residence time divided by the volume. So let's go ahead and write that out again. Flow, residence time, volume. So our flow rate, we were told, was 15 grams per hour. That's the rate at which it is being produced. And the residence time is 1 over K. So we'll just say 1 over 0.49. And then the hour is on the top, so those hours can cancel out. And then the volume was 40 cubic meters. So this is a matter of just some calculations here. And if you run these numbers through your calculator, I got 0.75 gram per cubic meter. Now, this unit doesn't necessarily mean very much to me, so I may want to convert this into parts per million. And in case you do, I want to remind you that unlike the aqueous sample that we talked about in the previous video, this is a gaseous sample. So we need to probably convert into moles. And this is possible for us to do because we know that this is grams of carbon monoxide and not just grams of some average pollutant that we don't know what it is. So what we want to do is moles of carbon monoxide divided by moles of air. And then we're going to remember that this is going to be in some kind of a decimal form. And if we want to go into parts per million from a decimal, we are going to multiply by 1,000,000. Just like when we go into percent from a decimal, we multiply by 100. Parts per million, we multiply by 1,000,000. If we wanted parts per billion, we would multiply by 1,000,000,000. So first you get it in the decimal form, and then you multiply it by whatever that factor is that you want to sort of scale it with. So let's go ahead and do that. So I'm going to start with my 0.75 grams per 1 cubic meter. And I'm going to give you the general idea here. And then I want you to pause the video and do it yourself. So the grams we're going to take into moles of carbon monoxide. And then the meters cubed, I want you to take into liters of air. And then let's go ahead and use the ideal gas law to go into moles of air. We need a temperature for this, and we're going to go ahead and make some approximations here. So we're going to assume, since this is just a garage, right, that this is probably at 1 bar of pressure, and the volume is just going to be per liter, so the volume can be 1 liter. So we'll use the R value that goes along with bars, and for temperature, we'll just pick room temperature. So go ahead and pause the video, take your time, calculate grams per mole, grams into moles of carbon monoxide. And what our goal is for us to have moles of carbon dioxide over moles of air, and then multiply by 1,000,000 to get parts per million. Okay, pause the video, and then rejoin me in a moment. Okay, hopefully you got something that looks like about 664 parts per million carbon dioxide or carbon monoxide. So if you did not get this number, if you got something pretty significantly different, I would just check your unit conversions. It's the most common way to do any mistakes in this area. And if not, you can always ask me during our class session. All right. Hopefully you're starting to feel a little bit comfortable with these flow problems. I know that this is a totally new kind of thinking and a totally new kind of material than what we're used to thinking about in chemistry. I've never looked at these values before either, so I keep having to look back at my equation. So I would recommend that you make yourself a little table, something like this one here, where you write down all of your different variables and just have a little list of them and how they relate to each other until you start to get a little bit more comfortable with all of these different variables. And with that, we're actually going to add one more variable to the mix. And this variable is called flux. So flux is not the same thing as flow. And if you've ever looked at physics or an engineering conversation, you've probably heard them talk about flux. So what flux is it's not just looking at the amount of flow like we were looking at right here, but it's looking at the amount of flow that goes through a particular area. So it's the units that it's going to have for flux. We're going to have flow per area, but what this is effectively going to be is concentration times speed. Okay, so let's go through how that happens. If we have flux is equal to flow over area, because we've got the amount of flow passing through an area, and that's what the flux is, then we can remember that flux is equal to the amount of stuff per time, and then we're going to leave the area alone. And the amount of stuff is the concentration times the volume, and then we still have time and the area. Now, if we think about volume as area times, I don't know, a height, I guess. It sort of depends on which kind of area we're thinking about, but we can go ahead and just approximate it like that, length times width times height, that sort of thing. Then that volume can become area times height. And by the way, you do not have to remember this process. You can just stick with this equation. But just in case you were curious, I wanted to show you how we got from one to the next. So our areas are going to cancel out. And then height is sort of the same thing as length or distance. And so height per time or distance per time is how we think about velocity. And because we have a V for velocity or for volume over here, I'm going to use a little cursive V to try and distinguish the velocity or the speed. It is really just the speed from the volume here. Okay, so to sum up, our flux is our flow over an area, or the concentration multiplied by the speed at which the stuff happens to be moving. So the best thing for us is to look at some examples again. So if we think about stuff and how the flux can manifest, we're going to look at an example of some aerosolized lead over Lake Erie. I think the author of this textbook must live in the Northeast. So lead used to be present in a lot of gasoline. And nowadays, of course, it's been discontinued in the United States at least. And so you still see as an artifact in gas stations, you still see unleaded gasoline. I don't think I've ever, well, it was being phased out when I was pretty little. There probably were a few cars at that point still where you could buy leaded gas. But anyway, basically all cars now only take unleaded gas. So the amount of lead that is being aerosolized through combustion reactions is pretty small. However, you do have other sources of lead from other industrial practices. So this could still be a relevant problem. All right, so our aerosolized lead has a concentration of about 11 nanograms per cubic meter. This is a concentration, right? We've got a quantity over a volume, so we can tell. And an estimated, this seems like a huge number, 21,000 kilograms are deposited in Lake Erie per year. I mean, it's a big lake, but still, that seems like a lot. So we want to know, what is the deposition velocity? Or what is the speed at which lead particles are being deposited? So if you are having a hard time sort of visualizing these, I recommend drawing a picture. And so it often helps me to draw a picture to think about what the compartment is and what the math is that's actually taking place. So if we think about Lake Erie, we were just told a surface area, or excuse me, we were not told a surface area yet. Here it is. Our surface area of Lake Erie is 25,700 square kilometers. It's a pretty big lake. So we have a surface area for this lake, and we are using this. This is our area, right? And so our flow is going through the surface of the lake, and that gives us our flux. So the flux would be equal to the flow over the area. And we also note that the flux is equal to the concentration times the speed. So if we look at the information we have, we do not have the flux, but we do have the concentration. We do have kilograms per year, that's the flow, and we have the area of the lake. So this is just a matter of a little bit of algebra. We're going to divide out the concentration and do a bunch of unit conversions. So why don't you go ahead and pause the video here. You can use your flux of 21,000 kilograms per year. Your flow of 21,000 kilograms per year. Your concentration of 11 nanograms per cubic meter, and your area of 25,700 square meters. Do your unit conversions. And let's all head toward units. Well, I guess the most sensible unit first would be in meters per year. That's probably the easiest one for us to get to. All right, so pause the video, take your time with this unit conversion, and then come back together in a moment. Okay, when I did this, I got 7.4 times 10 to the 4th meters per year. I don't have any kind of clue for what this number really means, because over the course of a year, I can't conceptualize this. In fact, speeds are a little bit hard for me to conceptualize anyway. So if you convert this unit again, then if you convert it into centimeters per second, for example, you will get 0.24 centimeters per second. And this, I have a little bit of a better idea of what that means, right? 1 centimeter is about this much. And that means that each lead particle is going about 1/4 of a centimeter in each second through the lake. So through the lake surface, or toward the lake surface. And that sort of makes a little bit more sense into my brain. I still am not totally sure if my brain knows what to do with this number. But hopefully this is starting to feel kind of okay. So we're going to look at one more example in this video before we stop, and then we'll move on to another topic in our next video. So the next example that I want to look at is one where we've got more than one source of the pollutant. So we can kind of look at another example where we combine them. All right. So this is looking at a combustion product from incomplete combustion reaction. So anytime you have a car that's not burning super efficiently, you get a number of organic compounds that are present in the exhaust. And we generally just sort of call them VOCs. This particular one is benzopyrene. Benzopyrene. And it's just abbreviated BAP, which is not to be confused with BPA, which is another pollutant. Anyway, they have the same letters, but they're not the same. Okay, they're different order. So benzopyrene is one of those nasty things that's a human carcinogen, so we need to pay attention to it. And when it gets into air, it can do things like falling like a particulate, sort of ash-like particles. And it also can get absorbed into rainwater. And so if we think about a lake as a system that materials are going to fall into, right? We've got the potential for water that is runoff, both into and out of, but we're going to just kind of assume that these happen to be steady state, and so we don't really need to worry about runoff. It's not really going to add to anything, although perhaps in a more complicated scenario we'd want to. But instead, let's just think about those particles falling into the lake and rain falling into the lake, both of which contain this source of benzopyrene. So this means that if we want to calculate the total flow of the BAP into the lake or into a body of water, then we need some information. So let's set up this scenario. So this scenario is built over Lake Superior. See what I mean about this guy being in the Northeast? I guess, is that considered Midwest? I'm such a Northwesterner, I'm sorry. So if we look at the BAP, we find that in rainwater, we have a concentration of the BAP of about 2 nanograms per liter. And as a particulate, in the air, we have about 5 picograms per meters cubed. And I just want to remind you that pico is 1 times 10 to the minus 12. Okay, so 1 picogram is 1 times 10 to the minus 12 gram. All right, so the surface area of the lake is 8.21 times 10 to the 4 square meters. And what we also need to know is the amount of rainfall. So this is a number that you can look up, and it turns out that it's about 80 centimeters per year. All right, so if we're thinking about the total flux, we're going to remember our flux equations. Our flow is what we're looking for, not flux. This is, I'm sure, going to be a little bit confusing, so I'll try and be really clear. Flow is our concentration, or excuse me, our stuff over the residence time. Also, our stuff multiplied by the rate constant. Also, our flux times the area. Also, our area times the concentration times the speed. All of these are expressions for the flow. Let's go ahead and separate these two components. So if we are first going to start with the flow for the rain, then we have our concentration, our area, and our speed at which this is deposited. So this is our 2 nanograms per liter, and the surface area of the lake. And the rainfall is 80 centimeters per year. So if you do some unit conversions there, I'm going to just skip to the answer here. But I hope that you pause the video and work it out. You should get 131 kilograms of the BAP per year being deposited through the rain. And for the particulates, for this we need to know how fast the particulates settle on the water. And it turns out that that answer that we got for the lead particles turns out to be pretty accurate. So for the lead particles, we found that the speed was 0.24 centimeters per second. Or you can do it in the meters per year, whatever you prefer. And then our area is the same, 8.21 times 10 to the 4 kilometers squared. And in this case, our concentration was 5 picograms per cubic meter. We need to get to the same units here, and if you do some unit conversions, I think you should get to 30 kilograms per year. So that would mean that our total flow of this BAP pollutant into the lake was the sum of these two. And so that would be a total of 161 kilograms per year. Again, hopefully you're starting to feel a little bit more comfortable with flow, that you now understand the difference between flow and flux. And make sure that you pay attention to these different ways of expressing flow, but they are really all part of the same system of equations, okay? So all of these equations are ones that relate to the flow in particular, but they all, all of the different pieces kind of relate to each other as well. So you should see another homework assignment that involves some of these more complicated problems going up pretty soon. And in the meantime, good luck with all of your calculations.